pleasure to get to speak to you. I'll tell you a little bit about myself. So I am an astronomer. A little more specifically, I'm an observational astronomer, which means that I go to telescopes and actually make measurements of stars and galaxies, as opposed to maybe a theoretical astronomer who's more sort of working at the whiteboard trying to derive the laws of physics, say. Although that distinction gets increasingly blurred these days. So these are just some photos of myself with some of the telescopes that I've worked on, and then maybe you can see from some of my lab or clean room photos here. I've actually been involved in projects to develop new instrumentation for telescopes. Maybe I'm just not satisfied. There wasn't anything on any telescope in the world that was good enough to make the measurements that I wanted to make, so I had to just go build something new myself.
Absolutely.
I'll come back to that a little towards the end of the presentation, but I thought I would just lead into that. So my research focuses primarily on exoplanets. So what are those? If you're not familiar with the term, an exoplanet is simply any planet orbiting a star other than the sun. And I've heard it said recently that that is perhaps a confusing title. What would be easier would be to just call these things planets and our 8 planets solar planets. But this is a theme, right? Astronomers are very good at a lot of things. They're terrible at naming things. And this is a problem when I speak with younger audiences. When I show them pictures of planets like this, the first thing I always ask is, what are their names? And I have to say, well, this one's B, this one's C. They get so disappointed. So this is actually a picture, an animation. These are pictures taken over many years and stitched together of an exoplanet system. And I'll just kind of lead off by saying it's not normally this easy. This is a very unusual system. And when we look at stars throughout the galaxy and look at their planet systems, we see a lot of unusual things. So some things to point out in this image. There's nothing to see here. That's indicating where the star is. But because the star is so bright, we've had to physically block the light so that we can see the planets in the glare. And the size of the hole we've had to cut, so this is 20 astronomical units. That's 20 times the distance from the Earth to the sun. And as a point of comparison, that's the distance at which Uranus orbits the sun. So we've blown out the entire solar system almost just in this cutout. And in this system, there are 4 giant planets. Each of these are more massive than Jupiter, several times more massive than Jupiter, and orbiting at distances where we have no planets in our solar system. So the galaxy is a strange place. I will point out the entire field of exoplanet discovery is just now hitting 30 years old. But it's not a new idea, and I love this quote from the Italian scientist Giordano Bruno in 1584. There are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our system. They only knew of 7 at the time. It is utterly unreasonable to suppose that those teeming worlds should be uninhabited and should not bear similar or even more perfect inhabitants. So now we're not only thinking about exoplanets, but thinking about life on those exoplanets. I mean, this is an idea that we're only now pursuing those boundaries right now. Unfortunately, in 1584, these types of ideas were considered heresy, and Bruno was executed for these and similar beliefs in 1600. Fortunately, public opinion towards exoplanet scientists has improved slightly in recent years. Otherwise, I would probably be in a different line of work. What took 410 years then? If we had these ideas already, what took 410 years to find these planets? The first one was found in 1995. And the reason is that stars are bright and their planets orbit very close by. Again, the animation I showed a moment ago is kind of the exception that proves the rule. So planets, in general, do not produce a lot of their own light. The light that comes to us from those planets are just reflected starlight. Just like when we go outside, the light that we use to see each other is just all reflected sunlight. And so when we look at a distant star and try to see the planets huddled up next to it, it's like looking into a lighthouse and trying to determine that there's a firefly just next to the lamp. So what do we do instead? Well, we have to look for indirect evidence. And I'll give the example, the indirect evidence that we're all pretty familiar with, where there's smoke, there's fire. So this is an image from 2011 in Texas. There was a bad wildfire season, and this is a satellite image. You can't see any of the fire directly, but you can see a lot of indirect evidence in the form of smoke. And I'll take a detour here to point out that this is one of the reasons why being an astronomer is maybe a more dangerous job than you might initially think. So this fire in particular included McDonald Observatory, where I conducted my dissertation research. This is the same fire just behind the Hobby-Everly telescope. This is the telescope that I used to conduct my PhD research. And at the moment this photo was taken, I was standing at the base of that telescope with a garden hose. I was not going to lose my dissertation or take more time because of a fire. So anyway, my point is that generally, in order to find exoplanets, what we have to do is actually look at the star itself, because that's where all the light, that's where all the information is coming from. And we look for some type of peculiar behavior from that star that indicates that a planet or one or more planets must be there. So to set this up, I need to sort of tell you what observational astronomers do. And there's two bits of terminology that I need to share with you. The first, there's really just two types of measurements that observational astronomers make. The first is photometry. And as the name indicates, we're just asking how bright something is. So we point at a star, how bright is it? How bright is it an hour from now, a day from now, a year from now? The other measurement that we might take is spectroscopy, where we take that same light coming from a star and we separate it into its different wavelengths or frequencies, and you might know this more intuitively as colors. And then we're sort of doing the same question, how bright is it? It's just a question of how bright is it at blue light? How bright is it in red light? How bright is it in infrared light? And this is all we do. This is kind of all we can do because it's unlike other sciences, other fields of science, we can't get up close and personal with our sample. We can't scratch it. We can't melt it. We can't smell it. All we have is the light that comes to us from millions or billions of kilometers away. And so it turns out there are techniques to find exoplanets hidden in the glare of their stars using each of these methods. So I'll walk through and try to explain those. So the first, I'll start with this one because it's the one that was used to find the first planets and the one that I used to find my first planets. It's called radial velocity, alternatively the Doppler technique. So this comes from the Doppler effect, where any object that's moving and emitting waves at the same time, the frequency of those waves will change. And so you've experienced this on the highway. If there's a siren on an ambulance screaming past you on the road, that change in pitch from the sound, those are sound waves changing frequency because of the motion of that object relative to you. Light is also a wave. It works the same way. And so if I'm watching a star, it has a spectrum that's like what's shown at the bottom of this image. So you have light in all colors coming from the hot surface of the sun, and you have narrow, dark bands that's caused by atoms or molecules in that star's atmosphere absorbing light. If that star is being pulled on by the gravity of an orbiting planet, then that star will move back and forth. I'll replay this video. So as the star moves back and forth, the frequency of the light waves emitted from that star are going to shift. And so the positions at which we see these dark bands, they're very helpful. They're like a ruler or something. They're moving back and forth. And and that is translating directly to the velocity of the star, the radial velocity. And so we can infer if there's periodic motion in those lines, then we can infer the presence of planets. This is really difficult, though. The animation I'm showing here is a gross exaggeration. So to give you a sense of this, these are small objects pulling on a very massive star. And so I've put some numbers on this. What are the speeds at which a star moves because of the gravitational influence of a planet? And I have to rag on this image from NASA. This is a graphic from NASA, and they've put speeds in miles per hour, even though everybody in science fields works in the metric system. So anyway, so the sun moves due to the gravitational influence of Jupiter, our most massive planet, at a speed of about 30 miles per hour, or in meters per second, which is what we use. It's about, say, 10 or 12 meters per second. The Earth is moving at quite a bit less than that. So to use the units that exoplanet scientists use, the Earth causes the sun to move at 10 centimeters per second. So if I actually try to walk that slowly, it's going to look kind of silly. And we're trying to measure these motions on a star that is light years away, all while its surface is roiling and bubbling like a pot on the stove with velocity fields of kilometers per second. Okay, I can throw numbers at you all day, and it may or may not mean anything to you. So let me try something else. Pretty much everybody in the room's got a camera phone on them, right? So you take a picture with your iPhone, there's a series of lenses that you see on the back of the phone, and that's focusing light onto a detector that looks like this. This is an array of silicon pixels. It's essentially converting light into electrical voltages. And if you take one of your digital pictures and you zoom in, you keep zooming in long past where the picture looks like anything, you see those little blocky shapes of color. Those are individual pixels. Those are individual little squares of silicon, and you can't get any better resolution than that because that's the size of the silicon onto which you're recording your image. And so that's what one of these devices looks like. So now I'm going to zoom in. This is an electron microscope image of one of those same devices. But this is 1/1000th of 1 pixel on that silicon device. Does anybody have any idea what these white dots are? It's not light. These are individual silicon atoms. This is the crystalline silicon lattice within your camera phone. So now, remember the animation I showed you of the shifting atomic absorption lines in the stellar spectrum. So now the question I'm asking is, how much will one of those absorption lines move due to a 10 centimeter per second velocity shift of the star? 6 silicon atoms. So that's the degree, if the device that we're measuring this with, we're sitting out in the parking lot, if you jumped up and down, you might move it more than that. We have to be extraordinarily careful in controlling what we call our measurement systematics when we perform this measurement. And we're really not quite to the level yet that we can make this measurement, although we're getting very close. So, okay, maybe this isn't the easiest way to do it. It's certainly not the most conceptually simple way to do it. And so for that, I'll switch gears a little bit, and I'll show you the transit photometry method. So this is, like I said, it's a little simpler. Remember, photometry, we're just asking ourselves, how bright is something? So we're staring at a star for as long as we possibly can, and we're just measuring how bright it is as a function of time. If we get lucky, and there's a planet orbiting that star at exactly the right tilt of its orbit so that it passes in front of the star, we won't actually see this, but we will see a slight dimming in the star that is due to the fact that there is a planet blocking some of its light. So this is just brightness as a function of time, and you see this kind of characteristic bucket-shaped dip. Now, this is also challenging, as you might imagine. Again, we've got big stars and small planets. So again, Jupiter, our largest planet, if we were to observe Jupiter transiting the sun would get dimmer by about 1%. Okay, that's doable. This is a simulation of the Earth transiting the sun and the measurements that we would make of the sun's brightness under realistic circumstances. And what we're trying to do, let's be clear, we're trying to count the number of individual photons, the number of light particles that hit a pixel in a fixed amount of time. And there's intrinsic uncertainty associated with this. So imagine you were trying to count votes. You were counting ballots for a vote. And just so we all stay friends tonight, let's suppose we're voting on something non-controversial or at least fun, like is a hot dog a sandwich? And suppose you had 1 million ballots to count. And the number of yes votes out of 1 million outweighed the no votes by 80. So 80 more yes votes than no votes out of 1 million. And you had to count that. You had to count it, and you had one shot at it, and you had to hold it all in your head. How confident would you be that you correctly counted the winner? Pretty low. That's the amplitude of the signal, the brightness signal of the Earth passing in front of the sun. 80 parts per million. This is what it would look like. And we've drawn on here the model to the data. But I ask you, if that weren't there, how confident would you be that there was a planet transiting in that data? This is really difficult. And also, look at the time scale. This is printed really small, but this is measurements taking place over a 24-hour period. Anybody see any problems with that?
Yeah, daylight.
Yeah, the sun comes up in the morning. That's the biggest problem, but we have clouds, we have wind, we have Elon Musk's Starlink devices flying across the sky. All of these create noise that far outweighs the signal. And so in order to play this game at all, we have to go to space. Radio velocities we can do from the ground because spectrographs are heavy. But if we want to do transit photometry at the level we need to find Earth, we have to go to space. And that's exactly what the Kepler spacecraft did starting in 2009. It was a spacecraft, not a satellite. It trailed Earth in its own orbit around the sun. It launched in 2009 and stared at one patch of the sky for 4 years. And actually, you can see above us, these are plotted in the crosses here, are all the known planets in the galaxy. And you can see this overdensity here. This is the field that the Kepler spacecraft stared at. It stared at one patch of sky. And you can go out tonight and see it if the clouds were to let up. There are two bright stars for our amateur astronomers, Vega and Deneb. And if you look directly between those two stars, that's the Kepler field. Each of these tiles here is one of those silicon devices. We used, I think it was 42 devices to record the light of about 150,000 stars simultaneously. You have to look at a lot. Just geometrically, the odds that a planet's orbit will be tilted such that we ever see a transit is only about 1%. So even if every star has planets, we only expect to see transits for 1% of them. So we watched 150,000 stars for 4 years trying to find transits. And we were really there were two questions we were trying to answer. The first is, how common are planets generally in the galaxy, in the universe? This was, in 2009, a question we really didn't know the answer to. And then more specifically, we're trying to drill down, okay, how many of those are Earth-like? How many of them are Earth-size in one-year orbits around stars the same size and temperature as the sun? Because that's really where we want to go if we're trying to find life elsewhere in the galaxy. So we took all of this data. It's one of the more impressive collections of data I'm familiar with in the world. And what we found, at least to answer the first question, planets are everywhere. Every star in the galaxy has planets. You go out tonight, you look at your favorite star in the sky, and you can rest assured it has planets orbiting it. This is a natural consequence of star formation. When stars form out of intergalactic gas, the planets form alongside it as a consequence. So this is just kind of counting planets discovered by Kepler, and this is not all of them. And in the years since, we've discovered even thousands more planets with follow-up missions like TESS, the Transiting Exoplanet Survey Satellite. But this is really interesting. There are a few things here. First of all, we see plenty of Earth-sized planets. That's really interesting. We see a lot of Neptune-sized planets, not very many giant planets. Those are a little bit rare. But we also see this weird thing, super Earth. What is that? That's a planet in between Earth and Neptune's size. It's something we don't have one in our solar system. And yet, from the statistics from Kepler, so keep in mind, this is only what we found, and we have to correct for all the planets that we didn't find because their orbital geometries were thrown off. It turns out this weird super Earth planet that we don't have one of in our solar system is potentially the most common type of planet in the galaxy. I'm telling you, the galaxy is a strange place. And what's weird about it is we may be the strange ones. The solar system may be the unusual case, not the ones that have these planets that we've never seen before. So I've been told if you go into a new class at the start of a semester or quarter and you feel the class is too big, write an equation on the board the first day and you'll cut it in half. But stick with me, okay? I promise this is the only math I'm going to subject you to tonight. So, all right, we'll start with a number that we've known for a while. The Milky Way Galaxy, where we live, contains about 100 billion stars, to put a round number on it. The statistics we pulled from Kepler, again, taking all the planets that we found and correcting for the ones that we didn't find but we know must be there, we find that each star in the galaxy, on average, should host about 2.5 planets. You multiply those two numbers together, and you find that the galaxy contains at least 250 billion planets. Now, I told you there were two questions Kepler was trying to answer. One was, how common are planets in general? Second is, how common are Earth-like, potentially habitable planets? And to be clear, what we're talking about is some small planet, rocky like the Earth. You need an atmosphere, but not too much, because otherwise the pressure gets so high that it'll crush us. And it needs to be orbiting a star at the right distance so that it gets the right amount of sunlight that the temperatures might allow for liquid water on the surface. That's what we're going for when we're talking about life elsewhere. We follow the water. The statistics we find from Kepler are that perhaps 25 billion planets in the Milky Way Galaxy might be Earth-like. And I should be clear, I think both of these numbers should be taken as lower limits. I mean, the solar system has a lot more than 2.5 planets. And there are well understood limitations to Kepler that tell us that there are a lot more planets there that we just weren't able to measure. So this is what I can confidently tell you must be there tonight. But we're pushing these boundaries further every day. And we're literally discovering new planets every single day. So I'll show a few of my favorites. I think I have time for this. Proxima Centauri. So have any of you ever been to the Southern Hemisphere? So there are a few like Skywatcher's treats in the Southern Hemisphere. One are the Magellanic Clouds, the dwarf galaxies that orbit the Milky Way. But the other is the Alpha Centauri system. This is the closest star system to our own, and those of us living in the Northern Hemisphere never get to see it. But if you've ever seen it, it really just looks like a bright light on the sky, and that's actually the Alpha Centauri AB pair. That's a binary pair of sun-like stars. But it's orbited distantly, that binary pair is orbited by a third star, Proxima Centauri, and as the name suggests, it's actually that third star that right now is the closest single star to the solar system. And it's so small and faint that even though it's the closest star, you cannot see it with your unaided eye. You have to have a telescope to see it. But when we look at it with a telescope, we find that it is actually orbited by, actually now we know of 2 planets orbiting Proxima Centauri. But one of them is just a little more massive than Earth, right in the middle of the habitable zone. And so if we're looking for potentially habitable environments, there's one next door. I can't tell you how exciting this is. This is close enough that we can actually talk realistically about sending spacecraft to take pictures directly. This is not a picture. This is an artist representation. But one day, maybe we'll get a picture like this from Proxima b. A few others. 55 Cancri E. This is one of my favorites. My PhD advisor discovered it. This is, again, a small planet. This is one of those super Earth planets. But it's orbiting incredibly close to its host star. So, as you might imagine, planets closer to their stars orbit in shorter periods of time. It just has less distance to cover. And to give you a point of comparison, Mercury, the closest planet to the sun in the solar system, the hottest planet in the solar system, takes 88 days to complete an orbit. So moving right along, a few months, and it's already, New Year on Mercury. 55 Cancri E orbits its star every 18 hours. I literally would sit up at night on a telescope and you could watch the orbit progress. I mean, it's unbelievable. And so it's incredibly hot. And something interesting about its star is it's potentially abnormally rich in carbon relative to other elements. And so we think that planets form out of the same material the star did. So we potentially have a planet that's especially rich in carbon under incredible heat and pressure. And it's believed that the entire interior mantle of this planet may just be diamond. If we could tractor this thing back to the solar system, we could put De Beers out of business. And this is not the only, we call these ultra short period planets. This is not the only one. Another one of my favorites has this terrible catalog phone number. KIC, that's the Kepler Input Catalog. And I won't even bother to read the number. You don't have to remember it. But this is another planet. It's orbiting a somewhat hotter star, and it's also in a very short period orbit. It completes an orbit in just 16 hours. And it's so hot that the entire surface of the planet is blowing away. This thing is a comet planet. And if it weren't, we never would have found it. This thing is tiny. The planet itself has been worn down to the size of Mercury. That is beyond even Kepler's measurement sensitivity. Well, we don't actually see the planet. We see the massive comet tail that passes in front of the star every time the planet orbits through. And I think this is a real interesting testament to the fact that the universe is a dynamic place. Nothing stays the same over time. We think of the planets in our solar system. We look at it and we see them night after night, and they seem like these perfect, unchanging bodies. But nothing stays unchanged in the universe. Things are always changing. They're forming, they're growing, they're dying. And here we see an entire planet dying before our eyes. On the other side of that, this one gets me really excited. Kepler 444. This is a star that is about 11 billion years old. Again, a point of comparison. We believe the whole universe itself is a little over 13 billion years old. So this is a star that's essentially as old as the galaxy. It's nearly as old as the entire universe. And yet we find that it's orbited by a system of 5 transiting planets. And these planets are probably not habitable. They're too close to the star. They're probably too hot. But I think it's really interesting to think about if the universe has been forming planets for 11 billion years, thinking beyond just finding life elsewhere, but intelligent life. Because we think single-celled life forms emerged almost immediately on Earth. As soon as the surface wasn't molten lava anymore, we had microbes. But thinking about what it takes to evolve intelligence, technology, if there are potentially planets that have been nurturing life for 11 billion years, it's more than twice as old as the Earth. It's fascinating and beyond any level of expertise I have to tell you about, but just to think about what types of civilizations might be out there. And lastly, you've probably seen this one in the news recently, TRAPPIST-1. This is another very small, very cool star like Proxima Centauri. And again, Kepler finds something like 2 transiting planets per star. TRAPPIST-1 has 7 transiting planets, 3 of which are in the habitable zone. So now we're not just talking about a planet full of life, but perhaps a system full of life. Could we have civilizations that are hopping back and forth from planet to vacation, to commerce, to learn from one another? It's unbelievable. So I can sit here and I can show you these planets and we can speculate what might be there, but of course we want to know, what is there? And this is where we look towards either the future or the very recent present. Some of you might have heard of this. This is a small pet project at NASA called the James Webb Space Telescope. James Webb is a significant upgrade over Hubble. So it's the largest mirror that we've ever flown in space. You can see its diameter is about 3 times that of the Hubble Space Telescope. And it expands our window into space from Hubble's optical wavelength coverage out into the infrared. And it wasn't necessarily designed with exoplanet science in mind, but it's certainly capable of some. And that's really pushing what we're able to go beyond, not just speculating anymore, but actually measuring what these fascinating exoplanets are like. And one of the techniques that we're using for this is called transit spectroscopy. So this is where we take a transiting planet, and again, planets themselves are dim, but we get a lot of light from their stars. And so the question then is, can we leverage that? The answer is yes. What we do here is we take a transiting planet and we look at the starlight that is actually filtering through that planet's atmosphere. And so if we compare the spectrum, the separated light from the star, before and during the transit of a planet, we may see a tiny bit of extra absorption in the spectrum that's being caused by light passing through the planet's atmosphere and being absorbed. So this is going to be one of our first windows into the atmosphere of an alien planet. So once we have that, what are we looking for? Well, again, if we're looking for life on other planets, we're looking for something called biosignatures. So these are features in the atmosphere of a planet that can only be caused by life. So here on Earth, the dominant components of Earth's atmosphere are nitrogen and oxygen. Nitrogen occurs naturally, but oxygen is only produced by life. Otherwise, we wouldn't see it. Oxygen is a highly reactive species. So if you release oxygen into an atmosphere and leave it alone without replenishing it, it'll react with other species and disappear. It'll react with carbon and form carbon dioxide. So it's only because trees are exhaling oxygen that we see it in our atmosphere. Methane is the same way. Methane in Earth's atmosphere is only produced by life. So this is just a diagram showing some of the features that we might see in the atmosphere of an Earth-like planet. And they include things like oxygen, methane, that are produced by life, but there are also signatures of things like water vapor that shows maybe not definitive evidence of life, but certainly some of the ingredients we need for a habitable environment. And transmission spectroscopy is not the only way to get that, but it's maybe the one that's most accessible to us now with things like the James Webb Space Telescope. We're actually doing this now. So I just introduced you to the TRAPPIST-1 system. James Webb is looking at the TRAPPIST-1 system like right now as part of its target list. And we actually have some results already for one of the planets, TRAPPIST-1b. This is just showing basically what we have as a temperature measurement. And we see here some predictions, also called models, for TRAPPIST-1, what TRAPPIST-1's temperature would be depending on if it had an atmosphere to recirculate heat from its host star or not. It turns out when we make the measurement, TRAPPIST-1 is pretty hot, and it's consistent with the prediction of what the temperature would be if TRAPPIST-1b did not have an atmosphere. So that's not necessarily surprising. This is not one of the ones that we were expecting to be habitable, so don't get your hopes too far down yet. We're not done with TRAPPIST-1 by a long shot. I should point out, James Webb is not certainly the only game in town. There are even more advanced facilities on the way. We're already thinking about, so James Webb was the successor to Hubble. We're already thinking about the next flagship space observatory, and that one would have exoplanet science built in from the ground up. And the reason for that, when you wouldn't imagine this, but when James Webb was first on the drawing board, the first exoplanets had not been discovered. So the people who did that can be forgiven for not putting exoplanets at the front of the line for science on James Webb. But this is a conceptual drawing, one of several concepts for what's being called the Habitable Worlds Observatory. So this is a space-based mission that is intentionally designed specifically to take images of potentially habitable exoplanets, Earth-like exoplanets, in nearby systems. So what might that look like? This is a simulation. If you take some mission concept like what I just showed you and picture the solar system 30 light years away and take a picture, this is what it might look like. So we've still had to block out a region of the solar system close to the sun because we have to get rid of that sunlight in order to see the planets in the glare. But we've done a lot better job of not blocking out the entire inner solar system. And so now we can see certainly Jupiter and Saturn, those big planets, but as we go just towards the inner edge of what we can see, we see those terrestrial-sized planets, Earth and Venus as well. And this is where we would go and measure spectra of those little dots and potentially look for biosignatures. We don't have to do this from space. Another project that I'm personally really excited about is the 30-meter telescope. So this is one of 3 telescopes in development that are going to have mirrors that are 30 meters across. So this is much bigger than what we can realistically put in space. And I'll show you here a comparison. On the right there, you see 3 of the mirrors that were at one time the biggest telescope mirrors in operation in the world. And Keck there in the middle, the 10-meter, that's still currently the largest single mirror in optical astronomy. And all of us astronomers, especially those of us in California who are partners in the Keck Observatory, are just climbing all over each other in order to get time on these things. But look at the TMT mirror. It completely dwarfs the Keck Observatory. And one thing that is particularly advantageous about these types of mirrors is they actually offer better imaging resolution than what something like James Webb could do, simply because the mirror is so big. And so this is especially useful for the closest stars to the sun. Stars like Proxima Centauri, they're overrepresented by those incredibly small, incredibly cool stars. And so the habitable planets are so much closer, and you need to get that much better imaging resolution in order to see them. Now, as I sort of implied a moment ago, time on those telescopes is going to be incredibly difficult to get. And the painstaking, time-consuming work of actually finding the planets that we want to take pictures of with the radial velocity and transit techniques cannot be done on those telescopes. There's just not enough time available. And so what we're trying to do today, right now, is find those planets and basically make a target list for those next generation facilities and say, look here, this is where we think the most exciting planets are going to be. And so this is what I've devoted the last, say, 10 years of my career to doing, is developing and using new spectrographs specifically to take radial velocity measurements at ever more sensitive levels and find those Earth-like planets. So I'm showing you here those two projects. On the left is HPF. HPF stands for the Habitable Zone Planet Finder. So it is installed on the 10-meter Hobby Everly telescope. That's the one I showed you on fire a few minutes ago. It's doing fine today and searching for planets. On the right, you see me with NEWIT. That's another spectrograph that we're using on the WIN telescope at Kitt Peak National Observatory in Arizona. And on both of those telescopes, I'm leading surveys of nearby stars where we're trying to monitor the same stars every night and make those ever more sensitive velocity measurements to try to find Earth-like exoplanets. And so maybe I'll leave you with this. This is hot off the presses. I'm letting you in on a secret tonight. So this is a nearby star. It's one of the 100 closest stars to the solar system. This image is actually to scale. So this is the representative size of the star. This green region is the so-called habitable zone. These are the distances from the star where we think a planet might have the right temperatures to have liquid water on the surface. And this is a system that actually one of my students has been studying intensely for the last 4 years. And what he has discovered is a very faint signal from what we believe is a planet that is just a little bit bigger than Earth, right in the range where we think it could be just the right mixture of rock with a little bit of atmosphere on top, right in the middle of that habitable zone. And this is one that we could, it's at the right distance from the solar system, the right type of star, that we could take that 30-meter telescope and take a picture. So the promise is paying off right now, and I don't know what's going to come next. That's what's exciting about it. There's something new every day, and I really appreciate the opportunity to come out here and share it with you. At this point, I'll just say thank you and take any questions you might have. Hands up everywhere. So I was told I need to wait for microphones to come around so everybody can hear your questions. So yeah, so she'll bring you a microphone.
Can you tell us the name of that?
Can you tell us the name of that last star?
I can tell you the name of the planet. It's C. Sorry.
No, it's okay. One more question. That first animation that you showed, those planets that were orbiting outside the Uranus orbit.
Yes.
How long are those orbits? Are any of them hundreds or thousands of years?
Yeah, so if I go, all right, I'm going to have to go way back here. There, you can see the date stamps on that animation. Sorry. So notice the date stamps. So this is approaching 10 years. And you see how much of the orbit is being swept out. It's a tiny fraction. So yes, these are hundreds of years long.
I have a playground voice. I don't need that. I gotta do it. On your planet C.
Yes.
Makes your heart go pitty pat, right?
Yeah. No, seriously.
How long before you get the right kind of instrumentation to that location? Are we talking 40 years, 400 years, 4,000 years?
So the timelines on these telescope construction projects are always a little fuzzy, and they only slip in one direction. But we're talking decade timescales, closer to decade than century timescales.
I'll find out when I'm up there.
Okay.
Hi, thank you for the lecture. In looking for signs of life on other planets, could it be that you're looking for signs that parallel life here, and that could be the wrong signs that you're looking for?
Absolutely. The problem is when you are in a galaxy of 250 billion planets and 25 billion Earth-like planets, that's a big search space. And so the question is, where do you start? And it's difficult to speculate on life not as we know it. There are some really creative chemists and biologists who are thinking about alternative metabolisms. How might life support itself in a really hostile environment like Saturn's moon Titan, which actually has an atmosphere and surface liquid, but it's not liquid water, it's liquid methane and ethane and natural gas. But that's difficult, and predicting what the signs of life would be and how unambiguous they might be. Even something like oxygen, we can come up with ways that a planet's atmosphere might present oxygen in the absence of life, at least temporarily. So it's a really difficult problem, and given infinite amounts of time, yes, we'd like to look everywhere, but if you give me a space telescope tomorrow, something like the Habitable Worlds Observatory is limited by things like fuel. How long can it continue to swing around the sky and point at different stars? We're talking about potentially getting a chance to observe 150 stars. That's it. And so if I have to pick my 150 best shots, I'm probably going to go for the Earth-like ones. One up here.
Okay, back to Planet C.
All right.
How was this discovered? Because if you're blocking out the star, what are you looking for? Radial velocity or
Yes.
or possibly wobble technique? That you are.
Right. So this planet that I showed you just now was discovered with that radial velocity wobble technique. We're not to the point yet of blocking out the star and trying to take a picture. So we know, something about what the planet's mass is and how far it is from the star, but there's a lot we don't know yet.
Yeah, that's what I was going to ask you next. What else do we know? We know something about the mass. We know something about the velocity. Yeah.
Right, so when we measure that wobble, the two characteristics we measure are what is the amplitude of the wobble, how fast is the star swinging around, and then so that tells us about the mass of the planet, and then there's the orbital period, what's the period of that periodic behavior, and like I said earlier, that corresponds to the distance of the planet from the star. That's just Newton's laws of gravity, basically. So those are the two pieces of information, and I will kind of caution you to kind of temper your excitement when you see these sensational news headlines that say Earth-like planet discovered. Those are the only two pieces of information we typically know at first. So again, it's an interesting candidate for detailed follow-up, but we can't go home tonight and say, job's done, we found Earth 2.0, we can all go home.
Right. Well, yeah. Headlines like that sell newspapers.
Absolutely.
But, there's another question for you, something that biochemists kind of speculate about. I hate to be impartial to everybody in the audience, but we're all carbon-based life forms. What about life based totally around something else? Something other than carbon?
Sure. It's a topic frequently discussed in science fiction, which,
Yes.
and I don't say that dismissively. A lot of times science fiction authors really know this stuff, and they are more likely to go out on a ledge and say something in writing that a scientist might not.
Because when you think about carbon, and is in the periodic table, being, I think it's in group 5, the other elements that have similarities are like silicon, but what would a silicon-based life form look like? Would we even recognize it? Of course, silicon doesn't have characteristics of wanting to bond really well. Carbon does. Yeah, it likes to join up with everybody. Yeah.
Right. Yeah, so and I'll advertise freely. I'm not a chemist or a biochemist, so my understanding of this is somewhat limited, but yeah, there are significant disadvantages of silicon, specifically relative to carbon. And I think the question is just, like anything else in science, can you make a testable prediction? If somebody can come and say, hey, I've got a prediction for a biosignature from silicon-based life forms, and it's much stronger than oxygen. Oxygen is a difficult atmospheric species to detect for several reasons. So potentially there's something easier that we could go detect tomorrow with the Keck telescope and not have to wait for TMT. That would be great, and it's something I'm sure astronomers would jump on.
Thank you.
Is this on? Okay. When we looked at the Kepler candidates, it looked like there were 955 Earth-sized candidates. And,
Right.
And did I hear you correctly that that's 1% of the planets that we can observe because they're in the that happy area where they're transiting in front of the sun, in front of their star?
Right. So, yeah, sorry, let me finish your question though.
Yeah, no, the question is that only 1% of what we think is probably there if we were to extrapolate that data out? Like, or potentially times 99 that?
Yes, so there's at least 100 times that many. And this is, again, just out of the sample of 150,000 we were looking at. So we find, to put a round number on it, 1,000 Earth-sized planets, multiply that by 100, it's 100,000, basically one per star. And again, those are just the ones that we're sensitive to. One of the things that we learned, and I didn't talk about this at all yet, one of the things we learned from Kepler is that the sun is an especially quiet star. So all the kinds of bubbling, roiling, things like sunspots, we've got this big spot on the surface of the sun right now. Other stars like the sun tend to have a lot more of that variability, and that makes it even more difficult to detect those transiting planets. So we get a factor of 100 increase just from geometry, but there's an even greater increase on top of that just because we know that there are some planets that are transiting and we missed because our measurements weren't sensitive enough.
Thank you.
Yeah, absolutely.
Hi, if I remember correctly, when you were talking about Alpha Centauri, you said that that's basically the closest Earth-like, potentially, planet that can be explored, and you said something that, we might be sending something there to explore. Is there a plan to send something to explore that potentially Earth-like planet?
Yes, there is at least a notional plan called Project Starshot, and this is the brainchild of the Russian billionaire Yuri Milner. And the basic idea is to send a fleet of spacecraft called light sails. So you take a very lightweight reflective sheet and you put a very small payload on it, something like the inside of your cell phone stripped down and made as lightweight as possible. And you accelerate it to something like 10% the speed of light using a very powerful microwave laser. So light actually imparts pressure on an object as it reflects off of it. So if you shoot this very lightweight sail with a very powerful laser, you can accelerate it to high speeds very quickly. And so this would be a one-way flyby mission. You would get some tiny fraction of a second in the Proxima Centauri system, take pictures real quick and send them home. But this is something that is, we're a long way away. There are a lot of technology milestones that have to be hit first. We have to develop the spacecraft, we have to develop the laser system, we have to get better batteries to store power to drive these lasers. So there's a lot that goes into it, but we are thinking about it.
Well, if it's a project
Well, perhaps so.
Hi, thank you. I have two questions. One is the 30-meter mirror.
Yes.
I need a better sense of the scope of that or the scale. And in addition to that, is it in one piece?
No, it's not in one piece. And I think that's the most important thing to help you visualize this. And I apologize, I'm flashing through things so quickly. So these mirrors, so the 5-meter Hale mirror that I'm showing here is a single monolithic piece of glass. But even starting with the Keck mirror, that's tiled in a hexagon pattern, kind of like a honeycomb. So it's made up of a collection of small mirrors, maybe about 1 meter across, that's in a hexagon shape, so you can easily tile them together. And so you see the numbers here. So the TMT mirror will have 492 of those individual segments. And that gets around the manufacturing challenges. It would be impossible to manufacture a single piece of glass that would be a mirror like that. It also allows us to very finely control the shape of that mirror. So as we turn the telescope to observe different targets, gravity will cause the whole structure to sag, and so it'll fall out of shape. And so we can use motors to adjust the position of the individual segments in order to keep the mirror in shape. And it also helps if observatories are notorious for being full of moths, and they tend to do their business on our glass, and it makes it a lot easier to swap out individual segments, clean them, put a new one in.
So is that 30-meter one just a sample of one of the tiles that would make the 30-meter, the TMT one?
No, that's a representation. So they haven't done a good job of showing the stitch lines between the segments, but that's what the entire mirror would look like, all tiled together. So if you want to get a sense of what one of these segments would look like, you can see this is the lower 3 sides of one of the hexagons on the Keck mirror. So you can imagine that kind of extending along this area to form one of the segments.
You could show JWST again.
Yes, thank you. You're right, absolutely. So this is the JWST. JWST uses the same mirror technology and there's an additional reason for that is because we have to fit it into a rocket fairing so it folds up onto itself.
My part to this question is, I feel related, but I'm not sure you will. You're looking at exoplanets and trying to find something similar to planet Earth. And we have these people on this planet right now trying to move to Mars. I need to know why people want to do that and why. I'm just going to stop with why, question mark.
Well, I know Buzz Aldrin has been asked the question of, does he think that we'll eventually send people to Mars? And he said yes. And when they ask him why, he says, because it's there. And that I don't think that's flippant. I think that speaks to the human spirit of exploration. It's the same reason people climb Mount Everest or take submersibles to the bottom of the ocean. If it's accessible, people want to go. And I think that goes beyond science. And so I can sort of speak to the relative value of sending one crewed mission to Mars versus sending 1,000 robotic missions in terms of the science yield, but this goes beyond that. I think if you're talking about developing Mars as an outpost for humans to live long term, I'm more skeptical of that. And I'm fond of the Neil deGrasse Tyson quote on that. For much less than the cost of making Mars Earth-like, you could just make Earth Earth-like again. And I also think that there are serious, potentially insurmountable challenges for permanent human settlements on Mars, but all of those are dwarfed by the challenges of trying to put people on exoplanets. And I want to be clear that I certainly have no intentions or thoughts that that is what's going to happen with these planets. I'm purely interested in learning what's there from afar, and I think that's where it's likely to stay. I know, I'm going to get your workout tonight.
The 30-meter telescope, where's it going to be located, and what is the estimate for first light?
So the 30-meter telescope is intended to be built on Mauna Kea in Hawaii, kind of just next to the Keck, the twin Keck telescopes. There are some challenges. There is some local resistance to putting another telescope there, and so there is actually a backup site in the Canary Islands, and the uncertainty over where the telescope is going to be located adds uncertainty to when the telescope is actually going to be built. So, yeah, I'm sorry, I couldn't give you a number tonight that I would feel confident about.
Thank you.
Okay, so I don't know if I can explain this right, but I kept thinking, like, from what you've been seeing so far in your researches, have you seen any unusual orbits, like that very first slide there where you had, I guess, A, B, and C? Mm-hmm. I was thinking about them, like going with the two methods that you talked about, for example. Have you detected or seen any unusual orbiting patterns? Can you do that? Can you pick out can you figure out like its ellipse size, or or one thing's like, no, it's off angle a little bit versus the normal plane of the star's solar system in a sense?
Yeah, actually, there are a lot of orbits that we've observed that would seem unusual to us, but again, the galaxy is full of strange things, and so in the bigger picture, I don't know if they're all that unusual. So to give you some examples, we've seen orbits that are quite different from Earth in the sense that Earth's orbit around the sun, fortunately for us, is very circular. So we stay at approximately the same distance from the sun at all times. We've seen exoplanets with orbits that are highly elliptical, and so they spend most of their orbit at great distances from the star, and then once per orbit swing in incredibly close and get blasted with stellar radiation. Their orbits are a lot more like comets than planets in that regard. Some other examples we have seen, so I said with transits, we get a transit every orbit. And in a lot of cases that's true, and in some cases it's a close approximation. There are planet systems where the planets orbit so close to each other that the planets tug on each other gravitationally, and they cause timing errors. So the transit of the planet will be 20 minutes early one night and 20 minutes late a few months later. We call them transit timing variations. And so it's the planet's mutual gravitational interactions that are throwing things off.
Roughly how much do you think fidelity or resolution loss do you think you lose to the stitching on those mirrors versus if you could theoretically make a mirror one solid chunk that size?
Okay, great question. So it turns out the resolution is not set by the amount of glass you have there. It's just set by the diameter of the telescope. And so there's actually a technique called interferometry, where you can take separate telescopes and move them some distance apart. And if you combine their light carefully, you can actually get the imaging resolution of a mirror the size of the separation between the telescopes. Now, it won't collect more light than the size of those telescopes. But if you add up the amount of surface area lost to those gaps between the mirror, it's negligible. There's actually, so I'll give you a fun example. There was a telescope that I used a lot as a grad student at McDonald Observatory in Texas. It's a 2.7 meter mirror. And when it was first commissioned, a member of the observatory staff had a bit of a breakdown and fired 3 bullets into the mirror. The glass of that mirror was a foot thick, and so it did not shatter as the person intended, but rather just left a few chunks taken out of the glass. They smoothed it out and recoated the mirror, and it's just fine. It's such a, even 3 bullet holes are such a tiny fraction of the overall surface area of the mirror that it's fine.
Okay, a question related to the first one I asked about the transiting planets that could take hundreds or thousands of years around the star.
Yes.
I asked that not to ask you to get into conspiracy theories, but is there a possibility that that could be happening in our solar system, that there's a planet so far out that we don't notice that?
Certainly, and I understand one of the earlier speakers in this series, Konstantin Batygin, was talking about that. So this is the proposed Planet 9 in the outer solar system that you may have heard about in the news. And what's happening there is basically we noticed patterns in the orbital properties of some of the distant asteroids and comets in the solar system, and potentially can imply from that that there's some gravitational disturbance that's happening from a distant planet we haven't identified yet. I think it's unlikely that planet would be multiple Jupiter masses like what I showed here. And in fact, the predictions are that the planet would be several times the mass of the Earth, which would be kind of interesting because that puts it in that super Earth category. And maybe the solar system has one after all, we just haven't found it yet.
How long would that orbit be?
Oh, that orbit would be hundreds of years.
All right, I have a question.
All right.
So you're an expert on disturbed stars, it sounds like. That's pretty great. My stellar astronomy teacher is an expert on degenerate stars.
Okay.
So my question to you is, we've obviously come a long way in terms of what we can detect based on those disturbances in the stars. How close are you, or what interests do you have in discovering future characteristics such as, I don't know, the magnetic field, moons with magnetic fields, anything else that's of interest and coming to you?
Yeah, this is of great interest because once we find these Earth-sized planets, let's say, assessing their habitability and whether or not they're actually inhabited by life becomes a much more holistic pursuit. And so understanding things like, does the planet have a magnetic field, and how does that magnetic field interact with the magnetic properties of the star is very important. One of the things that protects us on the surface of Earth from harmful solar radiation is Earth's magnetic field. And this is one of the challenges. You talk about going to Mars. Mars does not have a global magnetic field. And so astronauts living on the surface of Mars would be subjected to extreme levels of solar radiation. And that, I think, sets a definitive upper limit for how long you can safely stay on Mars. And so, yeah, it's long been the case as well that in order to understand anything about the planets you're discovering, you have to really know the star in detail. I mean, if you want to know how massive the planet is from how much it pulls on the star, you have to know how massive the star is, just to give an example. A lot of us who work in the field of exoplanets actually spend a lot of our days studying and trying to understand their host stars as much as anything.
Recently, there was a Dyson sphere discovered, or candidate. How much effort is going into looking for things like that?
Okay, so let me back up a little bit and explain to anybody who doesn't know that term what a Dyson sphere is. So this is a conceptual idea. Humans as a species, if there's one thing that we've done consistently throughout our existence, it's consume energy. So we consume energy at an exponentially increasing rate. Every year we use more energy than we did the year before. And if you project that forward in time, you see that very soon we will arrive at a point where we are consuming every photon of energy that falls to Earth from the sun. Ultimately, that's the only energy input to our system is the sun. And so the only way to get more energy at that point is to go out into space and put the solar panels that are on your roof, put them out in space and start collecting more sunlight than what falls to the surface. And so if you take this to the complete extreme, you end up with the Dyson sphere, where you have completely enclosed the star in energy collectors. So what would that look like? Well, we don't want to keep that energy and store it indefinitely. That would burn us alive. Think about your light bulb. You get a lot of useful energy in the form of optical photons out of that, but you also get a lot of heat, waste heat. And so if you're collecting a solar energy output worth of energy, you're going to need to radiate that energy away eventually. And just like the heat that's coming off of your light bulb, we would do that in the infrared. And so if we're looking for Dyson spheres in the galaxy, what we're looking for is a point source of light that is emitting a sun's worth of energy in infrared wavelengths, but basically none at the wavelengths that you can see. And so there have been some studies, and they typically use data that are collected for another reason. So for example, the WISE Space Telescope surveyed the entire sky in infrared wavelengths. Well, they were doing that to try to understand stars and galaxies, but why not piggyback off of that and see if there's anything compelling there? So I think this is something that is becoming more and more mainstream for astronomers to feel comfortable talking about and studying without being kind of seen as kooks. And so I think we're just sort of scratching the surface of what I would broadly call the search for technosignatures. So we're looking for some evidence, not just of biology, not just oxygen in the atmosphere, but some kind of technological behavior that a civilization is manipulating its environment in a way that doesn't occur naturally. So are we doing some? Yes. Is it enough? Probably not yet. Looks like there's one or two more up front and one in the back.
So getting to know the characteristics of the host star is becoming really important to us.
Right. So the question was, yeah, getting to know the host star is important. There's a mantra that kind of circles through the exoplanet science field that goes, know thy star, know thy planet. And it's not just to understand the planet, but to find it at all. Like I said, the noise, the variability that the star creates is now the limiting factor. Our instruments are so good that they're not the problem anymore. It's really the star that we're trying to get past.
Hi.
Hey.
Is it? Oh, yeah, there we go. I was just curious, are there any challenges that you may encounter due to the fact that our universe is constantly expanding outward?
Yeah, so I think that is a challenge to try and understand in general. But when we're talking about trying to find and understand exoplanets, we're talking about the only ones that we are able to do that for are the very closest stars. And the reason for that is stars get fainter the further they are away from us. And it's only the closest and brightest stars where we actually get enough photons from the star to make these very sensitive measurements. And on those distance scales, the gravity of the Milky Way Galaxy wins out over the expansion of the universe. So fortunately, it's not a problem that we have to deal with. Yeah, lucky us. I can't deal with one more thing. One all the way in the back.
Okay, so obviously it's very difficult to already find these planets, right? But how important would the influence of another body be on the planet, such as our own, because of like our moon's influence on the tides and everything, and the movement of the water on our planet? How important is that in actually potentially finding life on a planet outside of our own solar system?
Yeah, this is one of the things that keeps me up at night, really. So the Earth is unusual among the small planets of the solar system in that it has a moon that's a significant fraction of its own size. And yes, it controls the tides, and I think that's important, but I think more important is its impact on the climate. So some of you may be aware that the Earth's rotational axis is tilted about 23.5 degrees to its orbital axis. And that's actually why we have seasons on Earth. It's not that the Earth is getting closer to the sun or further away. Like I said, it stays at pretty much the same distance. But at different times of the year, your local area on Earth is tilted more or less away from the sun. And so it's getting more or less direct sunlight. And it turns out having the moon stabilizes that axial tilt so that it stays more or less at that sort of 20-degree range. If you compare that, say, to Mars, Mars does not have a massive moon. Mars has a couple of captured asteroids or comets or little dinky things that don't do much. And Mars's rotational axis flops all around. It goes from straight up and down to all the way over on its side. And so if you look at the seasonal variations on Mars over thousands or millions of years, the differences are much more extreme than they are on Earth. And so I think if you're talking about microbial life, pond scum doesn't care. Pond scum, can deal with some harsh winters and all that. But if you're talking about taking thousands, millions, billions of years to develop complex, intelligent, potentially technological life forms, I think that stable climate is going to be a lot more important. And so, if you're talking about where to look for civilizations like our own, I think maybe something like a moon might be important. And that's a little scary because we think Earth's moon formed when Earth suffered a collision with a Mars-sized body at just the right angle to shear off some material that formed the moon without completely destroying the Earth. And how many times is that going to happen in the galaxy? I don't know. My screen's going off. Yeah. We'll see if it comes back. Okay. Okay.
What is your favorite moon and why is it Ganymede?
So this question was baited a little bit. We were talking before the presentation here. I actually have a cat named Ganymede. In general, I'm fascinated by the moons of Jupiter and Saturn. So if you're not aware of this, yes, the moon on Earth causes tides, and that's a general effect. So if you look at moons in other planetary systems, there are tidal forces that come from the gravitational interactions between the bodies. In the cases of Jupiter and Saturn, those planets are so massive that rather than having like water slosh around on the surface, the moons of those planets are getting physically stretched and compressed by those tidal forces. And you can think about it like if you've got a glob of silly putty in your hand, you take it out of the refrigerator. It's like cold and hard. But if you start stretching it around, it warms up. So there's energy being deposited into these moons. And the moons, some of them are made up of significant fractions of water. And so these moons have liquid water oceans underneath their surfaces. And to put some numbers on things, Europa, the moon of Jupiter, it's believed that its subsurface ocean holds twice as much liquid water as on the surface of Earth, just in this little moon. So I think exoplanets are a really exciting frontier, and it's a really great mission to look for life there. But the first places we're likely to find life are here in the solar system, either on Mars or in these moons around Jupiter and Saturn. So that's why I get excited about moons like Ganymede. All right. Well, thanks everybody. This has been great.